Welcome to the second lesson for this unit. We're really going to start to think about properties of atoms here. Our unit essential question was, how do the properties of subatomic particles determine the different chemical properties displayed by atoms of each new element? And so we're going to really focus in today on how do subatomic particles determine the properties of atoms, which is really kind of part of that question. I want to just break this down a little more. If you notice at the end of the unit essential question, it talks about the different chemical properties displayed by atoms of each element. So the atoms of different elements of hydrogen and oxygen and nitrogen and gold, these elements all behave somewhat differently. The reason why is because of subatomic particles and the properties that the subatomic particles display and the numbers of each type of subatomic particle in different elements. And we'll explore all that today. The first concept then is to differentiate between the average atomic mass and the mass number. The mass number is the number of protons plus neutrons for a single atom. The mass number is always a whole number, and two atoms of the same element might have different mass numbers. That I don't think is in your notes. You probably have that from one of the POGL activities we did. But anyway, we'll look at what is in your notes now, the average atomic mass. And you are still responsible for knowing mass numbers. So if you want to write that definition down, I would go ahead there. The average atomic mass takes into account both the abundance and mass of each different isotope. So what that means is that the average atomic mass is a weighted average mass of all the atoms in a naturally occurring sample of an element. The mass number is just looking at one. The average is looking at all of the different isotopes. But you can't just add the different isotopes' masses together and divide by the number of isotopes, because there might be a different abundance of the different types of isotopes. That's going to be really similar to the way we calculate our grades, with the summative grades weighing 70% and the formative grades weighing 30%. So we'll have to multiply each isotope mass by its abundance, and then we'll add the abundances, or we'll add those numbers that we get the products together. Before I show you the calculation, I just want to look at what an isotope is, or what they are. They are two versions of the same element with different numbers of neutrons and different mass numbers. The difference between two isotopes of the same element, and I emphasize that we're looking at two isotopes of the same element, they're going to have a different number of neutrons and a different mass number. I won't always be as specific as that, but if I talk about differences and similarities between isotopes, I mean two isotopes of the same element. Different number of neutrons, different mass numbers. The similarities are going to be that they have the same number of protons and thus the same atomic number. Of course, these are the same element. They're just different versions of it. I prefer if you don't talk about electrons for these isotope questions as either a difference or a similarity, because the number of electrons we'll see, that's going to relate to whether an element is an ion or not, but it's not really relevant for whether an element is an isotope. And so that's why we don't really want to talk about electrons here. As far as the calculation goes, you'll get questions like this. If hydrogen has three isotopes, hydrogen 1, hydrogen 2, and hydrogen 3, and their abundances are given to us, we see the percentages there, we're going to calculate the atomic mass. So probably the easiest way to do this is to just take the mass times the abundance. So 1 times 99.983, 2 times 0.015, 3 times 0.002. Then we add the three products together to get the 100.015, but we divide by 100, and I get 1.0015 AMU, which means atomic mass unit. If you look at your periodic table, you should see an average atomic mass similar to that for hydrogen. And you can always check your answers like this. They should always be fairly similar, if not exactly the same. If you get something different than that, it means you probably made a mistake. The biggest mistake is that there's actually another way to do this problem. Instead of dividing by 100 at the end, a lot of students prefer to divide each of the abundances by 100 because what we're really doing is we're taking the 99.983% and we're converting it to a decimal, 0.99983. And of course, that makes sense to a lot of people mathematically. You have to do that 3 times. You have to divide each of those input terms by 100. The problem is that some students, when they do it like that, forget, and then they divide by 100 again at the end, so they get an answer like 0.010015. If you check the periodic table, you know that's incorrect. Similarly, if you forget to divide by 100 in either place, then you end up with 100.015. You should check the periodic table and realize that can't be right. Oh, what did I do? I must have forgotten to divide by 100 to get the answer that should look similar to the periodic table. So we'll see problems like that on the quiz and test. This chart here is very, very important. So this pulls together all the information that scientists concluded about the subatomic particles. The electron, the proton, and the neutron. We can see symbols there that we'll use a lot, E-, P+, and N0. Now, if you look at the black numbers here, the charge is negative 1.6 times 10 to the negative 19th coulombs, which looks like a very, very small charge. We see it's negative, and we see it's something to the negative 19th power. That's a very small number. But if you look at the mass of the electron, the mass is much smaller. So the charge is actually a very strong charge compared to the mass of the electron. You also might notice that the proton's charge is 1.6 times 10 to the negative 19th, which is exactly the positive of what the electron is. Now, you can see how these numbers all get kind of confusing. So scientists said, let's just call the electron -1. Let's call the proton +1. Let's call the neutron 0. Those are the blue numbers. The mass then, the proton and neutron have very, very similar masses. Something times 10 to the negative 24th power. The electron is times 10 to the negative 28th power. So that's a huge difference, more than 1,000 times, or very close to 1,000 times smaller than the proton and neutron. So basically, scientists said, let's just call the proton and neutron 1. Let's call the electron 0. Most times that's going to work. So you guys are going to need to memorize the blue numbers on this page. The black and red numbers will be given to you if you need them, which we will in a couple situations. But again, they'll be given to you. So memorize the blue, you'll be given the rest. The next thing we're going to do is look at a subatomic particles chart. So here I'm going to give you, well, sometimes I'll give you the chemical symbol and ask you to gather information from that. Other times I'll ask you to write the symbol from the information given. So first we got to understand the chemical symbol. You have the elemental symbol. You can see in the first example, like Na is sodium, that's the symbol. What do the numbers around it mean? The atomic numbers in the bottom left, the mass number in the top left, and the charge in the top right. Now, I'm actually going to exit out of this for a second, so that way we can see how I would fill one of these charts out. I'll make it a little bigger here. Hopefully that helps. So for my first example, I'm going to get the atomic number right away. That's the number in the bottom left corner, and it's also going to be on the periodic table. Sodium always has an atomic number of 11. It also always has 11 protons. So I like to get that information first because it's the easiest. We should never really make a mistake on that. The mass number, in this case, is given to us as 23. And interestingly, the atomic number does not always need to be given because you should know from the periodic table that it's 11. So even if this atomic number was not here, you should have still been able to get the 11. You do need to have the 23 given to you. We have to have that from the problem, or we can't really figure it out. Now, the number of neutrons is always going to be, and this is a little bit of inverse math here, the mass number equals the protons plus the neutrons. So if I just take the mass number minus the number of protons, I'm going to get the number of neutrons, which is 23 minus 11, which should be 12 if I'm doing my math correctly. The electrons now can be pretty tricky to get as well, but we see the charge there is plus 1, and that means that there's going to be one more positive proton than there is negative electrons. So some people think this means that we need to change the number of protons, but we can't ever go change the number of protons. So if there's one more proton, that means this element has actually lost an electron and it has 10 electrons. We go to example 2 now. The atomic number is 3, so that means that the number of protons has to be 3. In this case now, the number of neutrons is going to be 7 minus 3, which is 4. We haven't been given any information about the charge. When that's the case, we're going to assume the charge is 0 and it's neutral. That'll happen from time to time. We're expected to assume it's neutral unless we're given other information. So in this case, then the number of electrons would be the same as the number of protons, which is 3. And now we can write our symbol. We got to look at the periodic table. The third element, the element with the atomic number 3, is lithium. That will always be true. The mass number here is 7. And I'll put that up in the top left corner. And then we can put the atomic number in the bottom left. We don't have to. But the charge does need to go in the top right unless it's 0, in which case no charge is written. So that brings us to the last example here. In this problem, the atomic number is always the same as the number of protons, so let's get that right away. That's 8. The mass number is protons plus neutrons, so that's 18. And then in this case, the charge is also 0 here. Let's go ahead and say that instead of having 8 protons, let's say it had, instead of 8 electrons, let's say it had 10 electrons. Now the electrons outnumber the protons, so the charge is going to be -2 because there are 2 extra electrons. If I look to the periodic table, this element is going to be oxygen. It's got a mass number of 18. We know the element is oxygen, and then we know the charge here is -2. So that's how you'll do these types of subatomic particle problems. So just to quickly run back through what we've done, there's a lot of stuff that you should be able to do today. You should be able to differentiate between average atomic mass and the mass number. You should be able to tell me the differences and similarities between isotopes, calculate the average atomic mass of an element, identify the numbers in blue here, the charge and mass for the proton, neutron, and electron. And just to review from the other day, you should know that the proton and neutron are in the nucleus, and the electrons orbit around the nucleus. And we should now know how to complete one of these subatomic particles charts. So that's all for today, and we'll see you for the next lesson.